Module 1, Lesson 9, Tables of Equivalent Ratios. So we are going to continue to explore equivalent ratios, and we are going to look at it using tables. All right, learning targets. Well, we are going to be making some comparisons, meaning we're going to be writing some ratios, but mostly we are going to be focused down here, reasoning about comparisons, making predictions. We're going to organize our thinking and represent our thinking using a table. I can write ratios to represent real life situations. For example, we're going to go mixtures or constant rates, and we'll talk about what those things are. And we're also going to create a ratio table to help answer questions, solve problems. All right, example 1. To make paper mache, that pasty stuff that you use to make layers of newspaper stick together to make cool things like piñatas and models of the earth. To make paper mache, the art teacher mixes water and flour. For every 2 cups of water, she needs to mix in 3 cups of flour to make the paste. And down here in italics, we have our to-do. We need to find equivalent ratios for the ratio relationship 2 cups of water to 3 cups of flour. So we have a ratio here. For every 2 cups of water, she needs to mix in 3 cups of flour. And we are going to find some equivalent ratios, and we are going to represent them in the table on the right. So in your workbook, you should have a blank table. If you don't, get a piece of scratch paper. And let's go ahead and make the table here. Now, the first thing we're going to need is we are going to need to put some titles on some columns. Cups of water and cups of flour. And I'm going to leave the third column blank. I'm going to hang on to that for the next slide in the lesson. If you wanted to, you could potentially call this third column that I have created the total number of cups in the mixture. But I'm going to hang on to that third column because I want to look at something else. And we know that the ratio is 2 to 3. And we've got 4 more rows in our table that we need to fill with ratios that are equivalent to 2 to 3. And a tape diagram would make this really easy. I didn't leave myself a lot of room for drawing, so forgive me. 2 and 3. So right now, when I write 2 to 3, I have a 1 in all of my units, so a constant of 1. I could put in a constant of 2, which would give me 4 to 6. I could put in a constant of 3, which would give me 6 to 9. And I could put in a constant of 4, and 4 would give me 8 and 12, and I could put in a constant of 5, and 5 would give me 10 and 15. So I could use a tape diagram to help me complete the table. And hopefully you also noticed that what was happening on the table here is we had a times 2, and then a times 3, and then a times 4, and then a times 5. And we did the same thing, of course, on the other side. Times 2, times 3, times 4, and times 5. And of course, that's what a constant means. I'm multiplying both parts of the ratio, the cups of water and the cups of flour, by the same number. So I've got what I believe are a stack of equivalent ratios here. And I'm going to click forward to the next slide here. And I want to take a moment and actually look at what I have here on the table. And I need to analyze, what can I say about the value of the ratios in the table? What is true about all of these values? Well, if I'm going to answer that question, I need to find the value of each of the ratios. And you remember from the last lesson, the value is the ratio written using the largest possible units. So this first one I know has a value of 2 to 3. Now the 4 to 6, I've got the 4, 1, 2, 3, and I've got the 6, 1, 2, 3, 4, 5, and I can put them into the groupings of 2, and that will tell me that the value is 2 to 3. On 6 to 9, I can look at this a different way. I've got the 6 to 9, and they will both divide by 3, which would give me a ratio of 2 to 3, which is a value of 2 to 3. I could also look at it this way. I have a value of 8/12. The cups of water is 8/12 the cups of flour, and I can divide both of these by 4, which will give me a value of 2 to 3, or 2/3. And I could do the same thing with 10/15, divide them both by 5, which will give me a value of 2/3. Now I know it seems kind of silly. I mean, we just went through and when we made the table, we multiplied up by 2. By multiplying up, I mean we scaled. We multiplied by 2, so we scaled up. We made more mixture. Well, with the value, what we did is we scaled back down. If we were to simplify our mixture down, what would happen? As we go through the lesson, on every one of the tables we look at, we're going to go back and we're going to ask what is the value of each of the ratios, so that we can make the statement, the value of the ratios in this table, they are equivalent. We're using tables of ratios to find equivalent ratios. So it's really important that we come back and connect to, hey, all of these ratios are equivalent, and we can prove it. All right, example number 2. Javier has a new job designing websites. He is paid at a rate of $700 for every 3 pages of web content that he builds. And we are going to create a ratio table to show the amount of total money Javier has earned in ratio to the number of pages he's built. So I know that I've got this rate of $700 for every 3 pages. So I've got 700, total number of pages built. I've got 3 pages is $700. And now I could double, and I could have 6, and I could have 1,400. Now, some students would say, okay, now I'm going to double the 6, and I'm going to put 12 and 2,800. And there's nothing mathematically wrong with that. But I always like to go back to my original ratio. I like to always come back to this ratio here and scale from there. So I want to take 3 and I will multiply it by 3, and 700 and multiply it. 3 multiplied by 3 would be 9. And 700 times 3 would be 2,100. And then I could multiply by 4 and get 12. Multiply by 4 and get 2,800. Multiply by 5 and get 15. Multiply by 5 and get 3,500. Multiply by 6 and get 18. Multiply by 6 and get 4,200. Multiply by 7 and get 21. Multiply by 7 and get 4,900. Multiply times 8, get 24. Multiply by 8, and I will get 5,600. Now, one of the reasons I go back to the original ratio, you'll notice when I doubled the 6 and got 12 and 2,800, I had skipped the 9 and 2,100. And then if I had doubled the 12, I would have skipped all the way over the 15, 18, and 21. So by going back to the original ratio, the 3 to 700, and scaling up from there, I'm not going to miss some stuff. Now, there's a whole discussion about using decimals and fractions and things like that. Right now we're scaling with whole numbers, meaning we multiplied by 2, 3, 4, 5, and 6, but maybe I could multiply by 1.5. And of course, then I would have something in between the 3 and the 6. All right, so I have a beautiful table of equivalent ratios. At least I believe they are. And it says Javier is saving up to purchase a used car that costs $4,200. And how many web pages will Javier need to build before he can pay for the car? Well, it's great that I've got a table of equivalent ratios here because I can just read along here, and when I find $4,200, I can find the matching amount, and I can see that Javier is going to need to make 18 web pages before he has the $4,200. A little bit of careful erasing there. All right. Now, the value of the ratios in the table. Well, the value of this first one is 3 to 700. Now, on example 1, I showed you a whole bunch of ways to find the value. So go ahead and try those out, practicing finding value. But when you're done, you should find that every single ratio has a value of 3 to 700, or 3 700ths. So what can I say about the value of the ratios in the table? They are equivalent. All of the ratios in the table are equivalent. They have the same value. All right, exercise 1. So spraying plants with cornmeal juice is a natural way to prevent fungal growth on the plants. We make cornmeal juice by soaking cornmeal in water. And this is a mixture. We are going to use 2 cups of cornmeal for every 9 gallons of water. So this would be a time when, if we actually look at, like if we try to total here, we're adding cups and gallons. I can't just add these numbers together and say that I've got cup gallons. So as you talk about mixtures, it's important to look at the units that you're working with. Another reason to not be in a hurry to use a total column. And by now you've probably figured out that third column is going to have something to do with ratio value. All right, so it says 2 cups of cornmeal for 9 gallons of water. And now I'm going to scale up. I'm going to use some multiplication. I'm going to double, which would give me 4 and 18. I'm going to triple, which will give me 6 and 27. I'm going to quadruple, which will give me 8 and 36. And then I'm going to quintuple, meaning multiply times 5, 10 and 45. So now I have a ratio table that I can use to answer some questions. Now remember, that's called scaling up. When I have started with a ratio and I have multiplied to increase the parts. I started with 2 cups and 9 gallons of water, and I said, oh, that's not going to be enough. I need more mixture. So I doubled the recipe. Have you ever made cookies and doubled the recipe? That's scaling up. So we have scaled up here. So we have multiplied by a whole number to scale up. All right, let's answer some questions. So how many cups of cornmeal should be added to 45 gallons of water? Well, let me come over to my table here. I've got gallons of water, and I'm looking for 45 of them, which tells me that I should have 10 cups of cornmeal added to 45 gallons of water. And, probably ought to write that. 10 cups of cornmeal should be added to 45 gallons of water. All right, we're going to keep this moving here. All right, let's take a look at the next one. Paul only has 8 cups of cornmeal. How many gallons of water should he add? So I'm going to come over to my cups of cornmeal, and I'm going to come down and find 8, and I'm going to find that he should use 36 gallons of water. All right, here we go. What can we say about the values of the ratios in the table? And you'll see that I've added them. No, it's not in your workbook. We know the value of the first one here is 2/9, and we can take the 4/18, and we want to write it in the largest possible units. I can divide them both by 2, which will give me a value of 2/9. This dividing here is called scaling down. We're going from a larger quantity down to a smaller quantity. We're taking a big recipe and we're turning it into a smaller batch. Sometimes you've got a batch of cookies and you're like, oh, this is going to be way too many cookies. Not sure that's possible. But you want to make only a half batch instead, and so you scale down. And we find on this one we have 2/9, 2/9, and 2/9. We can say that the ratio of the value of all the ratios on this table are equivalent. What can we say about the values? They are equivalent, and we can prove it. All right, exercise 2. James is setting up a fish tank. He is buying a breed of goldfish that typically grows to be 12 inches long. That's a pretty big goldfish. It is recommended that there be 1 gallon of water for every inch of fish length in the tank. What is the recommended ratio of gallons of water per fully grown goldfish in the tank? So a fully grown goldfish could be 12 inches. And for every one of those inches, I would need a gallon of water. So if I've got a fully grown fish at 12 inches, I need to have a gallon of water for it. So if I've got one adult fish that's 12 inches long, I'm going to need 12 gallons of water. For every inch, I'm going to need a gallon of water. So if I've got one fish, I could have 12 inches, so I need 12 gallons. And of course, the fish might get lonely, so maybe I go and buy a second fish. I have just doubled the number of fish that I have, so I probably need to make sure I've got at least 24 gallons of water. And maybe those two are lonely, and so I go and get another fish, and now I've got 3 of them, and I would need 36 gallons of water. Now this is scaling up. We're increasing the quantities here. And I could have 4 fish and would need 48, or I could have 5 fish and I would need 60 gallons. Once again, this is scaling up. I have started with my original ratio, my ratio of 1 to 12, and I have multiplied both parts of the comparison by the same factor. The factor is the number they're multiplying by. I've multiplied by 2, 3, 4, and 5. And over here with the gallons, I've multiplied by 2, 3, 4, and 5. Scaling up. All right, let's see what questions they have for us to answer here. So what size tank in gallons is needed for James to have 5 full-grown goldfish? Well, I can come over here and I can find my tank that has the number of fish, and if I want 5 fish, I know that the comparative value is 60 gallons. James would need a 60-gallon fish tank for 5 full-grown goldfish. Now, if I've got a 40-gallon tank, how many full-grown fish can go in a 40-gallon tank? Well, let me look down my gallons here. And I've got a 36 and I've got a 48. But I don't have a 40, so now I've got to do a little bit of thinking here. Could I put 4 full-grown fish into a 40-gallon tank? Well, according to the ratios I have, I'm going to be 8 gallons short. One of the fish isn't going to have enough room. And it's not like we can really assign one fish and say, sorry, you don't get to have enough room. You can't grow longer than 4 inches, for example. So realistically, real life situation, I would have to back up and say if I've got a 40-gallon tank, I'm only going to be able to have 3 fish in the tank. So got to do a little thinking here about how we'd handle that in real life. Now, what can we say about the ratios? Well, on the table, and this is quickly going through, if I were to scale them all down, I would find out that they all have the same value. They are all equivalent. Oh, and not quite what I wanted to click there. Let me try that again. All right, and I think I've made a mistake on this next slide, so we'll see what it looks like. Oh, goodness. I think that's a little bit out of order here. So when creating a ratio table, what does each pair of values represent? Each pair of values represents a ratio that is equivalent to all the other ratios in the table. So by the pairs of values, I've got my ratio table, and maybe it's dogs to cats, and it's 2 to 3, and 4 to 6, and 6 to 9. Each pair, so the 2 and the 3, the 4 and the 6, the 6 and the 9, each of those represents a ratio. They're all three ratios, but all three ratios have the same value of 2/3, and they are all equivalent to the ratio of 2 to 3. They're all equivalent to each other. Goodness, I had a rough time making this one. All right, so the question here is, can you think of a situation where you've seen a ratio table other than here in class? And of course, I gave you a ginormous hint here. What about the back of a pancake mix box? And on the back of the pancake mix box, you can see here we've got 2 cups and 1.5 cups. And some pancake boxes will actually have a whole table where they will go through and they'll say, if you want to make this many pancakes, this is how much mix you need and this is how much water you need. So there are ratio tables in the real world around us all the time. Now, can you think of a table of numbers you've seen that was not a ratio table? Just because it is a table of numbers does not mean it is a ratio table. If we are going to say that it is a ratio table, we have to make sure that they all have the same value. So it's very possible, cats and dogs here, maybe person 1 has 2 cats and 1 dog, and person 2 has 3 cats and 1 dog, and person 3 has 1 cat and 2 dogs. So there's a table of information, cats and dogs, that doesn't have equivalent ratios. So it's really, really important that we don't overgeneralize. We don't just look at a table and say, oh, every table that we ever run into is a ratio table, because that's not true. We have to be smart enough, we have to make the decision to examine the table and ask, is this a table of equivalent ratios? All right, so what's a ratio table? A ratio table is a table of pairs of numbers that form equivalent ratios. So it's a table, and we have pairs of numbers, and those pairs of numbers are all equivalent. They all have the same value. Keep hitting that over and over again. I hope it's getting drilled deep into your brain. All right, so I can statements. I can write ratios to represent real-life situations. We looked at mixtures. We were mixing things together, cornmeal and water to make paste, and we did paper mache. And then we have constant rates. So we had Javier and his websites. He was getting paid $700 for every 3 web pages, or 3 web pages were equal to 700. Those are constant rates. The same with the fish, 12 inches for 1 gallon. And I can create a ratio table to solve problems. So given a real-life situation, create a ratio table that has equivalent ratios. All right, so learning targets. Well, we wrote ratios in this activity, and we reasoned about ratios using ratio tables. making some predictions. We did some scaling. So we scaled up and we scaled down. So that concludes Module 1, Lesson 9. So make sure you go ahead and do your problem set. If you've got any questions, make sure you talk to your teacher.